Okay, I think we're going to go ahead and get started. Let's see, so the midterm was Monday, and you probably all had nightmares about fish fossils. But that's a joke. We're not actually going to have a whole lecture about just fish. I think the midterm, at least grading the 3/4 of it that I graded, turned out pretty much the way I wanted it to. And if you think you missed a lot of points, hold the phone, don't stress out until you get your grades back, because I think the average grade is not going to be that much higher than about 50%. Maybe it'll be up to about 2/3. But if you think you scored that low, then don't panic. Let's see. So the last time we actually talked about material was Friday. And at that time, we talked about how to build coherent, filled-in 3D models from multiple sets of range data. So now we're going to talk about some of the more kind of, mathematically interesting stuff related to how you would use entire filled-in surfaces in practice. So just to review, we know how to acquire 3D surface scans. We know kind of the physics or the physical principles of it. We know how to get rid of noise out of them. We know how to align multiple scans together, and we can build them into 3D models. So what? Well, let's just say that you have done this, and you were so gung-ho about learning how to do this in class that you did it yourself, and you did it many, many, many times. Let's say you had a model car collection, and you scanned in all of your model cars and built complete 3D models of all your model cars. So, given a new 3D model that you scan, one thing that you might want to do is look for similar instances of it in your database. This is kind of a generic problem that is driven by several real-world applications. So, in graphics, you may want to do something like, how many people have seen Edward Scissorhands? So, okay, one of the kind of motifs of the movie is that Edward Scissorhands and his other people in the movie live in a kind of a dystopian suburb, where it's not just that every house is kind of similar to all the other houses in this suburb, but that they are really, honest to goodness, identical to each other. And that's one of the things that makes the movie so creepy, is that every house on every block is identical to every other house on every block in a kind of vast sea of no individuality. Okay, so if you are creating a movie and you want to basically render blocks with houses on them that look a little bit less creepy, you'd want to have some amount of variability amongst the various houses. So what you might want to do in that case is consult a 3D database of house models, plop one down on your street, and then look for other houses that are similar to it but not identical to. So neighborhoods tend to have this property that there isn't a brick castle-looking house next to a low-slung bungalow next to a brownstone 3-story house that's tall and skinny. They tend to be more or less similar without being identical to each other. So if you have a large model of 3D surfaces of houses, then you can basically query for similar houses to the one that you have just picked to decide what house to put next to the one that you picked first. In computer-aided design, it's very common for engineers, especially mechanical engineers, to want to build up complex mechanisms from a finite set of pre-existing parts. So if you are a automotive engineer, say, and you're building a new gearbox, you probably do not want to design each gear of the gearbox de novo. You probably want to the degree possible, pick a set of pre-existing gears that are already in use in other engines and build up your gearbox from those. So what you can do if you are one of these engineers is have a database of 3D models of gadgets like a transmission gear, or plumbing is another example, where all of those, it's like a catalog. You can pick one of these pre-existing shaped gadgets or gizmos or components from a large assortment of them. And however, you have your own notion of how your mechanism should be designed. So you have your own ideas about what exactly the gear ratio of your gear should be. And you have your own notion of what exactly the shape of your plumbing valve should be. So if you can mock up your own idea of what a particular gadget should be shaped like, then you can search for similar instances of it in your database of pre-existing parts, and then in that way kind of find a nice middle ground between machining everything from scratch and making a transmission that costs hundreds of thousands of dollars to machine, and having it do what you want. There's a more kind of practical, well, they're all practical, but this is more kind of punitive, I suppose. In copyright protection, you can actually, copyright law has gone kind of, has really stretched a lot over the years, such that you can be accused of copyright infringement if you build a physical artifact that is just plain too similar to one that is pre-existing. Even if it doesn't, if, for example, if IKEA builds a particularly distinctive shaped lamp, and you build another one that is not identical to, but highly similar to it, you can be slapped with a copyright infringement lawsuit. So if you work for IKEA and you want to protect your copyright on your distinctive kind of artsy, nouveau-looking Scandinavian-style lamp, then what you can do is basically either take a photograph or a 3D model of somebody else's lamp and see and check it against your database of existing lamps to see if it's highly similar to one that you've already marketed. And similarly, if you have a fairly distinctive, I don't know, couch or some other piece of furniture, you at IKEA can scan a knockoff that you see in a store to get a sense of how similar it is to the one that you're already selling. And keeping with the IKEA theme, you can do kind of the similar thing to what the automotive engineer did, but with the goal of doing interior design in your house. So you have your dream house, you have a sense of what the shapes and sizes of the various couches and end tables and so on should be, and so you can mock those up, basically build rough 3D models of them, and then compare those to pre-existing ones that are in the IKEA catalog. So these are all applications that are motivated by the idea that you have a kind of a query 3D model that is sitting in front of you, and you want to compare that to a large database of pre-existing complete 3D models. Does that make sense? Okay. So let's see. There are basically two different ways that you can, general approaches for how you can do this kind of querying of a database. The first is to exhaustively, it's kind of similar to the difference between exhaustively looking at every patch in a new image to see if it matches a patch from a pre-existing image that you already have, versus picking out the salient points. There's an exhaustive approach in which you have your 3D model that you are querying, and you have your 10,000 models that are in the database. Well, you can then individually compare your query model to each of the 10,000 ones that are in the database. Obviously, that is time-consuming. But again, it's exhaustive, and so if there exists a model in the database that is similar to your query one, you will find it and you will detect the fact that it is similar. The other approach is to do a sort of dimensionality reduction on that works the same way on your query object and on your database, on every object in your database. Which is to say, you have your 3D model, which consists basically of a set of point positions in 3D and edges that connect them to each other. So that you have some mapping or some function that takes one of those to a feature vector, basically a set of floating point numbers that in some way boil down the entire object to a set of salient characteristics. If you do that to every one of your 10,000 models in the database, and you do the same kind of thing to your query object, then basically what you can do is reduce your problem of finding similar shapes to finding vectors of numbers that are similar to each other between query and database. And there's a number of different data structures for doing that. That basically turns the problem into a proximity search in a vector space. So if you've taken an advanced data structures class, there are all kinds of different data structures for addressing this. Things like, if you've heard of KD trees, that's one. There are all sorts of different hash table type data structures that address this, bucket hashing, and so on and so forth. So, right. Well, but if you didn't want to go as far as to make use of an elegant and fast data structure, you could even be exhaustive and slow and basically compare your query vector of features to every vector of features in your database. That's the slow way to do it. But the reason why you would reduce your 3D model to a concise vector of features is so that you can use these fast data structures at all. So that's why you would do it, to make it fast. So let's talk about, yeah.
Sorry, with that. Using a hash table, isn't there like the possibility like a false negative, like that you'll never find something, like, so how do you fix that?
Well, you don't. You basically, the way you fix that is by exhaustively comparing your feature vector to all of them in the database. Usually, okay, so basically there's the theory and there's the practice. So the theory is that there's a function that maps vectors of numbers to bins in a hash table. And so in theory what you do is you apply that hashing function to every one of your 10,000 models that's in the database, and you apply the same hashing function to your query feature vector. Okay, so that's the theory. The problem is that there are boundaries between one hash bucket and the next. So in other words, you can have two feature vectors that are highly, highly similar to each other, and one of them just happened to land one hash bucket to the right of the other one, which means that you miss it completely if you simply search for matches within one particular hash table entry. So in practice, what you end up doing is kind of smearing your hashes around and not only mapping your query object to one hash table entry, but to several of them looking for matches, which is what makes the whole thing quite messy, in fact. Any other questions about this kind of hash table approach? Okay, that being the case, let's think a little bit more about these feature vectors, which you will often find referred to in the literature as signatures. And the idea is that, I don't know, when you sign your signature, in some sense, it is a very small, very concise summary of yourself. It's unique to yourself, largely in the sense that signatures are fairly unique to an individual, but it's not the entire sequence of your genome. It's a small, concise little thing. So that's why it's called a signature, is because it's supposed to, each one of these feature vectors is supposed to be unique to your object of interest in some sense, and it's also supposed to be not a huge amount of data. So the things that we want out of these signatures, first of all, is that they have this property that they're unique. That if you have two very, very different objects, they should probably have two very, very different feature vectors, two very, very different signatures. The second one is robustness, which is to say, imagine, and this, if you can wrap your head around this concept, imagine that we are able to continuously change two different objects to make them continuously more or less similar to each other. So if you can think about two objects that are on a line, where on one side of the line the thing is shaped like a banana, and on the other end of the line is shaped like an orange, so they took a sphere, say, and in the middle you get something that is not long and pointy and kind of crescent moon shaped, but that is more round and more blobby and more sphere-like. And if you imagine a slider like in a GUI, where all the way to the left is a banana and all the way to the right is an orange, and the thing in the middle is kind of this banorange thing, then what you would want is for your signatures to be more similar to each other the more similar the shapes are. So if you have a banana that's all the way to the left and something that's a little bit more orangey, but it's mostly a banana, you want the feature vector to not change very much in that transition. And in fact, ideally what you would want is for the feature vector, the signature, to change continuously and gradually as you slide your slider from banana to orange. Does this concept make sense? Okay, yeah?
And is this what you would call generative descriptive?
Yes. Well, so it depends on what you do with them. So you could take a similar approach to what we did earlier in the course and think of the space of signatures, the space of all feature vectors corresponding to all objects in your database, and then partition that space into parts of the space that correspond to banana-shaped things, parts of it that correspond to orange, and so on. On the other hand, you could also take a generative approach and say, what is the probability of me getting this feature vector given that the underlying shape is Mr. Banana? So it's a little bit orthogonal to that. But for right now, we're just talking about things that you want your shape signatures to uphold. So robustness, basically small changes in shape should lead to small changes in signature. Another one is we'll get back to this idea of invariance. And here, simply put, it might be desirable for your shape signature for a straight up and down banana to be identical to that for a banana that's on its side. Because in your mind, those are basically the same object in a different configuration. So it would be great if your shape signature did not change a lot or at all if you transform the object. And it's the same idea as earlier, where there is a class of transformations that you posit at the beginning. So you say, I want my shape signatures to be invariant to translation, rotation, and scaling. And then you construct your feature vector or your signature such that it has that property. But we also want ease of computation. So what I told you is that you calculate these feature vectors in the first place so that you can simplify the problem of proximity queries. So in other words, so that you can use a fast data structure to decide whether a query shape signature is similar to one from a large collection. Well, that's fine, but if it takes you an hour to just calculate the feature vector in the first place, then you've kind of overruled your speed advantage of going to a feature vector in the first place. So it should not take forever to calculate these things. And also conciseness. This goes back to the signature idea that, that a signature is both unique and not very large. And the reason for this has to do with that near ubiquitous rule of thumb for all you computer scientists, that the cursive dimensionality, that anything that you do in a higher dimensional vector space, on average, is going to be more difficult, more time-consuming, more space-consuming than if you were to do the analogous thing in a lower dimensional vector space. Not always true, but good rule of thumb. Well, and obviously, saliency is important too. If the two objects that you have in your database are a banana and an orange, then the entries in your shape signature should capture whatever property is the most banana or orange-like, or the thing that discriminates the two from each other. So we're going to focus on general purpose signatures, not ones that are specific to any particular domain like fruit. But there are other shape signatures out there that are more specialized. And in particular, they really don't make that much sense unless you apply them to particular kinds of shapes. Well, the most prominent example of this is biomedical shapes. So shapes that are extracted not from surface data, but from 3D medical imaging data. And we will talk about those later on, I think in 2 or 3 weeks. Okay, so let's talk about some ways of building these shape signatures. One prominent approach is called geons. It's really a traditional approach in many ways. It was developed in the 80s with no computation involved, really. It was more of a theoretical kind of a construct. The term geons comes from 2 words, geometric ions, geons. And the idea here is, if you remember high school chemistry, you can think of compounds as being built up of component parts called ions. And each one of the ions is sort of atomic in some sense that you don't consider them as being built up from their own component parts. They're kind of inseparable. So here we have geometric ions. And so just as one example, imagine that you have a geometric primitive, just one geometric primitive that is a cylinder. And your task is to describe any shape or any object model that you have by taking that geometric ion, that cylinder, and replicating it over and over and over again. And every time you replicate it, you transform it in some way. You translate it, you rotate it, you scale it, either isotropically or anisotropically, and you place them in the scene as your way of building up your description of your object. So if you do that, that might sound kind of silly, but in fact, you can actually get kind of coarse representations of objects just from one single ion, or one single geon, I should say. If you have a complete filled-in 3D model of an entire human body, you can do a fair job of representing it in terms of just a few of these cylinders. And if the arms bend, well, you just add 2 more corresponding to forearm and upper arm. And similarly, it goes all the way down the scale from arm to forearm to hand and so on. So then, if you take this approach and you are able to convert your point and edge representation of your object into this collection of geometric primitives, then your signature is very simple in a way. It's just a depiction of what the primitive is. You just say it's a cylinder. And then a set of geometric transformations that keep replicating it and placing it somewhere. So you scale it down and you put it there. You scale it down a little less and you put it there. You scale and rotate and you put it there. So that would be your shape signature, would be this description of how geons keep getting placed throughout the scene. Now, so beyond human beings, there are many different objects that can be represented just by doing this thing of replicating a cylinder over and over and over and over and over again. You can actually do a pretty good job with anything with limbs, like you can see those are mostly animals. Or they might be entirely animals. They're entirely animals. But you can think of other man-made objects that this applies to as well. And that's only if you restrict yourself to just one of these geometric primitives. Imagine that you add a couple more of them. So besides a cylinder, you also include a megaphone-shaped cone, an extruded cylinder that is curved, kind of like macaroni pasta, and a pyramidal solid and one of these blocks. If you do that, then you can actually tremendously build up a great deal more objects in terms of being able to build up all sorts of different configurations of object models. Things like telephones and briefcases and mugs and such. So again, what would happen here is that your shape signature would consist of the name of one primitive, like here's primitive number 3, and then a geometric transformation of it that places it in the scene. And then the next primitive maybe number 4, and the rotation and translation that places it in the scene, and so on. Does this make sense? Great. And one way to rephrase that is you start with an alphabet of geons. which is to say a discrete small set of these geometric primitives that you keep placing throughout the scene. And then that's an example like I've been saying. So it's an intuitive idea. That should be kind of obvious that that you can look at any object that you have in front of you and ponder the ways in which you could describe it in terms of a set of small number of geometric primitives. And it's surprisingly rich, the amount of things that you can describe this way. The problem, though, is that people have tried many, many times over the years to start with a filled-in 3D model of the type that we talked about building on Friday and converting that to a set of geons. And it has been hard, hard, hard. For some objects, the decomposition of the object in terms of a unique set of geons is very difficult. They're not robust at all, and it's hard to make them invariant. And in particular, imagine that you have one object that is made up of a collection of cylinder-like geons, and then another object that is part cylinders and part macaroni pasta-shaped things. How do you compare those two to each other? What is your distance measure that tells you how similar they are to each other? It's completely non-obvious how exactly you would compare an object that is 3/4 cylinders to one that is 2/3 cylinders and 1/3 extruded pyramids. It's hard to make them invariant to just about anything. If you take the same object and scale it up or rotate it, you might end up with a completely different description of the object in terms of the orderings and the transformations of its geons. And minor changes in the object can lead to entirely new geons being added. And just as one example that I just thought of, imagine that if you take a 3D model of my hand, you can imagine building up a geometric description of it in terms of a kind of a fat cylinder for my palm and then cylinders for each one of my fingers. Well, if I had a big wart on the back of my hand, you would hope that you would get basically the same geometric description of my hand before and after the wart. But probably what would happen in that case is that a new cylinder covering just the wart would be added to it. And possibly even worse than that, you might end up breaking up the whole palm into a wart part and then two separate cylinders on either side of it. Or something else for this area that has basically a cylinder with another cylinder cut out of it. So small changes in the object shape can lead to big changes in what the geons tell you that they are. Okay? Okay, so here's your administrative announcements for the day. We finished grading homework 1. And the average was about 37 out of 55. And the median is very similar. Standard deviation is about 7. So hopefully you know the deal by now that if you are within about a standard deviation of the mean, you're probably doing all right. Basically in either direction. If you're below that, then you should probably be concerned and try to do better. And Jing, have you posted the grades to SmartSite? So you should be able to access your grades for homework 1 now. And can you post an announcement to that effect? Great. About homework 1, pretty much everyone did part 1 really quite well. Part 2, I think a lot of people took basically just isotropic smoothing, which is fine. And some people, very few people, I think 2 people, just went to the extra step of rotating the patches based on where the landmarks are. So that was good. And for the third part, for picking interesting patches, what most people did was look at the standard deviation and pixel intensities. And if there's a greater standard deviation, then it's interesting. A few people did other stuff like look for the number of edgy pixels. But that was pretty much it in terms of heterogeneity. Any questions about homework 1? Okay. Homework 2 is out. Hopefully you have gotten started on it already. Oh, and actually, I think probably the number one way for one to lose points was to run out of steam on part 3. So it's fairly common, and this has happened over and over again in past iterations of the class, where homework 1, very solid, part 1 is very solid, part 2 is very solid, part 3 is kind of which suggests to me that you probably ran out of time. So if that sounds like you, then you should really start early on homework 2. And we are almost completed with midterm grading. So those should be posted to SmartSide by Friday. And the deal with the midterm is that you are more than welcome to come to my office and look at yours and the solution side by side, and we can make an appointment to do that if you can't make my office hours. I'll bring those to my office hours for the next couple times. But yeah, I was mentioning earlier that I think the midterm turned out the way I wanted it to, which is to say the mean grade is actually not very high at all. So something like between 50% and 2/3 of the number of points, which is really what you want if the course is being graded on a curve, because that means a curve is optimally fair if the mean is 50% and the standard deviation is about 20%. But you'll get those statistics on Friday. Any questions about any of this stuff? Okay, then let us move on to a different notion called shape histograms for getting a global shape signature. So here we say, forget about the idea of converting our point and edge 3D model into some other representation. Let's just represent it in terms of points and edges and try to extract characteristics of those points and edges. So shape histograms do something that's really almost exhaustive in its nature. For every pair of points on your surface, or for every triple of points on your surface, or for just a random sampling of pairs or triples, you calculate some geometric primitive based on those. Either if you can pick randomly 2 points on your object and calculate the distance of the line between them. You can pick triples of points and calculate the surface area of the triangle that they form. You can pick random faces and calculate the surface area of that. You can calculate the angles made by the triples of points. And so, for example, if you go with the distance option, then you will basically do this over and over again, thousands and thousands of times, for each object model. And that'll give you thousands and thousands of distances per object model. So you can make a histogram of those. And if you do that, then it's not going to be entirely obvious how the shape of the object maps to what the histogram looks like, but nonetheless, you will get histograms of those geometric primitive values that look like one of these. So if you have a two-dimensional circle-shaped surface, and you calculate, I forget which geometric primitive this is exactly. I think it's surface areas. Not entirely sure, but if you have a cylinder, your histogram might look like this. If you have a cube, your histogram might look like that. And then you can think about this histogram as being your shape signature. So if the histogram has 100 bins in it, your feature vector would have 100 numbers in it, where each number tells you how many geometric primitive values fell within a particular range. Yeah?
Doesn't this depend a lot on the distribution of the sampling points?
It does. And in particular, it doesn't seem very robust, especially if you simplify each instance of your object model independently of the others. So usually, when this is presented in a paper, it is assumed that you have a very dense, rich sampling of the entire surface regardless of curvature. So usually what we would do is if we had a surface model of this table, we would have very few points on the table itself because it's so flat. But where exactly you sample that surface, remember we have that discrete surface sampling problem that we've talked about previously, where those points might be is kind of up in the air. So usually here what you do is you assume that you have a very dense sampling of the entire surface, in which case you're removing that failure mode. So, like I said, it's not entirely, like, if someone were to give me a 3D object model and say, draw the shape of the histogram of point-to-point distances, I would not be able to do it. I wouldn't expect you to do it either. But please take it as an article of faith that these things are descriptive and that they differ across different types of objects. So here what they did is they took several different types of object models of animals, balls, helicopters, skateboards, and so on, and for each one of them calculated one of these shape histograms, for example, using point-to-point distances, and then superimpose these histograms on top of each other. So what you should see, I think they made their point here, that globally, there are pairs of object classes that have similar shape histograms to each other. And in particular, don't know why, claws and helicopters seem to have similar shape signatures. And similarly, what's another good example? Well, phones, planes, and rifles. For whatever reason that is. But there also is a range of different ones. So lamps are highly distinct from balls, are highly distinct from open books. The other thing that you should notice is that the shape histograms within an object category, like planes, tend to hang together. If the set of all planes were highly variable in terms of what their shape signatures looked like, this thing would look not like a general hump that goes up and down like this, but it would look like spaghetti. It would look like complete noise. But what you should see is that for every category of object, the set of all shape signatures within a category has a coherence to it. They all look similar to each other, which, if you think about it, is remarkable. For a large set of categories, there exists a thing that you can compute from them that is in common across the different instances. So, some pros of this approach is that they tend to be robust to noise and outliers and missing data. And the reason why is that you are building up your description of the object by many random pairs or many random triples. So what this means, if you follow the reasoning of it, if your object has 1,000 points in it, and you take 1,000,000 samples, and you compare that to the case where, say, 10% of those points are missing, well, then only some of those random samples would have hit the part that is now missing. So in other words, most of the point-to-point distances that you compute in the missing data case, where part of the object has been chopped off, is going to be exactly the same as if that part had been there. So it has this kind of gradual decay property that in some sense, if 10% of your object is missing, the shape histogram is 10% different. And if half of your object is missing, the shape histogram should be half different, because you keep taking these random samples across the entire surface. And it is probably true, although hard to prove, that the shape histograms change gradually as an object is changed gradually, kind of by following the same logic of random samples. So if you have your, let's say, a banana, and you have your original shape histogram that was built up from 1,000,000 pairs of points drawn from the entire banana, then if you stretch 10% of the banana, then something like 90% of those pairs of points didn't change at all. which means that 90% of the data that's going into your shape histogram hasn't changed at all. So it's kind of that same logic about building up a description from many, many random samples. So it should be clear from just how I described them that one of the downsides of shape histograms is that they're not the most intuitive thing in the world. You can stare at an object, you can think about how to calculate angles from it, and still not have any sense of what the shape histogram looks like. You can write code to take as input a surface mesh and give a shape histogram as output and be totally unclear as to whether you have a bug or not. Because these things can look like anything. There's no guarantees about how unique they are, and just to review, phones, planes, and rifles. One of the things that's unfortunate about this particular figure is that somehow objects that start with the same letter or similar letter tend to have similar shape histograms, like phones, planes, rifles, and then chairs, claws, and helicopters. I don't know why, and cars even. But and they are computationally intense to compute, and in fact, the thing that I just told you about how it's great that you take many, many random samples of points is actually a two-edged sword. So you actually have to answer the question of how many pairs of points do you need to calculate distances between in order to get a robust description of shape. And it should kind of smell like n squared, right? So if you have 1,000 points on your object and you want to get an exhaustive sense of what the shape histogram is, then you're going to calculate, 1,000 choose 2 of these distances, which is a lot. And again, we go back to our original point that, which is that calculating shape signatures in the first place was useful because it was fast. And if it takes you forever and a day to calculate the shape signature in the first place, you might as well not bother. Okay, one other entirely different approach to global shape signatures is to use what's called moments. So, hopefully, I think I've taken this poll already. You've all taken a statistics class in one form or another. So you know what the mean is. It's basically the average of x. And the variance of a distribution is the average of x squared in some sense. You subtract the mean out of it, but don't worry about that. Just, it's the average of x squared. And we all seem to stop there. We don't ever consider the possibility that it might be interesting to calculate the average of x cubed, or in the statistical notation, the expectation of x cubed. But you can. There's no reason why you can't. You can calculate the expectation of x to the 4th, x to the 5th, x to the 6th, and so on. And each one of those numbers will give you a more refined sense of how a set of data is distributed. And in fact, you can show, using a technique called the method of moments, that you can actually recreate an entire distribution of data if you calculate enough moments. It might take you infinitely many of those moments, x to the 10th, x to the 100,000th, x to the 400 millionth, and so on. But you can show that if you take enough of these moments, you can use them to back out exactly what the shape of your entire distribution of data was. So this is just another way of saying that moments are informative. So that's what happens if you have one-dimensional data, if you just have one number x. If you have two-dimensional data, it gets more complicated than that, where you can have basically moments of different order that correspond to taking different powers of x, the x coordinate of your two-dimensional variable, and different powers of the y coordinate. So this by itself, x minus the mean, taken to some power, should look like the mean and the variance. So if p is 1, so if p is 2, this is basically the variance of x. And if x is 2 here, that's basically the variance of y. And if you multiply those two together, that's the covariance of x and y. But in statistics, we usually stop there with P equals 2 and or Q equals 2. But you don't have to. You can have P go all the way up to 3, 4, 5, 6, and Q go all the way to 3, 4, 5, 6. So what you do end up doing in practice is then extending this to 3D, where you have x minus the mean of x taken to some power, y minus the mean of y taken to some power, and z minus the mean of z taken to some power. And you would apply this to your set of 3D point positions on your model. So the value of each one of those different moments is in some way going to give you a sense of the spread or the relative distribution of points in each one of these 3 dimensions and how they covary with each other. So one nice thing is that these things are translation invariant, and they can be made rotation invariant by combining the moments together in various ways, which I will not get into. What I told you about are what are called geometric moments, but there's a way to basically compress all the information that's in the geometric moments into a smaller number of numbers called either Legendre or Zernike moments, which again I will not, I don't think I'm going to have time to get into. But the point is that your shape signature for your object model is going to be the set of moments for your distribution of points up to some order. Does this make sense? Intuitively makes sense. Well, that's good. I promise I won't make you write this formula out on the final. Okay, so some of the things about moments, if you want, you can just think about representing your surface, your 3D object, in terms of a cloud of points and removing the connectivity data. Just it's a cloud of points, and you're calculating the covariance matrix of that thing. And then you're taking it a step further and calculating something like a higher order covariance matrix. So the pros of this thing is that they have invariances. They're the same no matter whether you translate them or not. They can be made invariant by combining them in various ways. And they're not that hard to compute. It's basically as hard as calculating a covariance matrix. They tend to be robust to little modifications of the surface. So they have this robustness property that if you have a set of moments for a banana and you make it slightly more orange-like, you should get a similar set of moments out. Problems here is that there's no guarantees that the moments for one type of object are distinct from the moments of another one. It's unclear how many moments you need to really richly describe your object to such a degree that it's distinctive from the other ones. And it might not be that intuitive in the same sense that shape histograms might not be. And in particular, if you have a program that is supposed to be calculating these moments, and you see that for a particular object, the P equals 5, Q equals 6 moment is large, what did you really learn? It's not clear.
Question.
Yeah?
So does this just use the point data and not the connectivity?
Yes.
Throwing away most or a good part of your information.
That's right. Yeah. So there's ways to make it even more complicated than this, which I haven't gone into, but this is what most people end up doing, actually. Well, okay. Let me just. Okay, good. Well, we'll talk about Gaussian images here just for a minute, and then you can look at my pictures of skeletal representations on your own time. So here, your global shape representation is going to be what's called a Gaussian image, where you start with a unit sphere and compute the surface normal of every mesh face. So here you do keep the connectivity data. And at every location on the surface, you calculate the surface normal. Well, if you think about it, each surface normal represents a direction in 3D. So if you have a 3D sphere, basically that direction maps to one location on that unit sphere. So for this thing, this direction here is going to map to this location on the sphere. this surface normal is going to map to that location on the sphere, and so on. So you can effectively convert your set of all surface normals to a sphere representation. And the Gaussian image is essentially doing that. It basically converts your set of surface normals to a sphere where the directions of all the surface normals are stored on the corresponding location on the sphere. So you can extend this. It's actually called the extended Gaussian image, where you attach surface information to each one of those surface normals. So if a face on the object is red, then you color the extended Gaussian image sphere red at that corresponding location where the surface normal points to. And so this sphere is then a kind of a sphere-shaped signature for the object model in this sense. It can be helpful representation for graphics because it helps you with rendering and you can read why. It tends to be fairly robust. It's invariant to translation and scaling because that doesn't change the directions of normals, and it's compact. But again, we have this thing that there's no guarantee of uniqueness. So I'm going to skip the rest and just summarize by saying for global shape representations, you have to worry about invariances, robustness, intuitiveness, and how easy they are to compute. And that's kind of your design choices for you to consider as the engineer. Any last minute questions? Okay, thank you.